So we want to know the partition function of our whole container full of molecules, not just of one molecule. The formula I showed so far is just for one molecule. I computed the vibrational frequencies of the one molecule. So now I have a whole lot of identical molecules. If I have like a gas cylinder, a whole bunch of molecules in there. And the formula for that, if they're not interacting, is the product of the partition functions of each of the individual molecules. So that would be like the q to the nth power, because if you have n molecules. And then it's divided by n factorial. Because the molecules are indistinguishable, you get this denominator of n factorial. And this is, again, a quantum mechanical thing, that if I take two hydrogen molecules, and they're here, and they wiggle around, and they end up here, I take a snapshot. I can't tell the difference, because hydrogen molecules look like hydrogen molecules. And so from the point of view of counting the states correctly to get the correct partition functions, I have to consider this distinguishability issue. And that gives me this n factorial. And people remove that n factorial. You know, I guess just remember, n might be like Avogadro's number, right? 6 to the 10 to the 23rd. And then you take the factorial of that. It's pretty big. Okay? It's a really big number. And so you don't want to do anything with that factorial. So you want to get rid of it. So the way that people get rid of it is you take the logarithm of both sides. And that logarithm, it gives you the equation I just showed here. And we use a thing called Stirling's approximation for the logarithm of a big number factorial. And so this is what it is. And this e is the 2.7, you know, the natural number. Is that what? Wheeler's constant? Is that what it's called? I don't know. Anyway, Wheeler's number. So this is what it looks like when I rearrange it. And so you'll see in a lot of the equations we have, logarithm of q is actually the thing that shows up in the thermo. So this is actually what we really need to have for the thermo. And this thing scales as n, how many molecules you have, which kind of makes sense. And these little q's are the q's from the individual molecule calculations we did already. And then we get this v over n factor at the end. The q trans we computed before had a v in it. So q trans over v, let's go back and look at that for a second. Here we go. So q trans is proportional to v. So it's pretty easy to just divide by v, and then you just left with this factor. Okay, so that was no trouble. So then you have q trans over v. This whole thing is all very simple to calculate. And then there's this v over n, which is like the 1 over the concentration. Or you can replace that if you want with kt over p. And if you're trying to compute normal standard state thermo, you should use p equals to 1 atmosphere. On the other hand, if you're trying to compute the actual thermo, like the actual chemical potential of your molecules at your real system, then you should use a real partial pressure of the species, because you really want the concentration of that, how many of those type of atoms. That's at the end are supposed to be how many of that particular type of atom. Okay. So some comments about this, about the system partition function versus the molecule partition function. I should warn you, both in my notes and also in many textbooks, people use capital Q's and little q's back and forth with no regard. So sorry about that. You have to like just tell by the infer from the context what they mean. All right, so this q trans over v appears a lot. And so a lot of times people just call that q trans. They just automatically divide out the v. That's just one thing to be aware of. Of course, if you do that, then your q has units per volume, whereas otherwise the q's are always dimensionless. But if you do that, then you can write that the logarithm of the whole system's partition function is n times the logarithm of the individual molecule partition functions times kt over p. We had this q electronic, which I haven't talked about. For a normal stable molecule, q electronic is just 1, so it doesn't even appear. For most free radicals, q electron is 2, so that's not too bad either. However, there's a few goofball molecules that have non-degenerate electronic states, some complicated thing. Maybe most famous one is like OH, I think O2. There's a few molecules that have strange Q electronics, and you have to go read a paper about that, about the individual molecules, and they'll tell you about what the electronic energy levels are, and you can compute the partition function for those. If the molecules are actually interacting with each other, so it's not an ideal gas, then you can correct this expression for Q using the equation of state. So if you have some empirical equation of state for your gas, then you can turn that back into the language of Q, of capital Q if you want, because capital Q is really telling you what the free energy is, and the equation of state, it's possible to compute the free energy from the equation of state. So you can calculate sort of the corrections due to real gas effects and include them in if you want in this thing. So this formula here is for ideal gas, because I used the ideal gas, I replaced V over N with ideal gas expression here. But instead, if you had a real gas, you'd have some other expression here, and you can make the corrections. But it's not that hard to do. However, for liquids, then the Q rotation and Q translation are completely different, because you don't have free translation anymore in a liquid, and you definitely don't have free rotation. The molecule can't just spin, because it keeps bumping into the other solvent molecules. And so those guys are changed a lot. But the Q vib, which is actually often the biggest term, is not really changed. Because if you do like infrared spectroscopy in the gas phase or in solution phase, you get like little tiny redshifts of the vibrational bands. The frequencies change a tiny bit, but it's really not a big deal. You still have the same vibrations in the molecule. Fundamentally, it's the same thing. The solvent's just a weak perturbation on the vibrations. So you can just use your gas phase Q vib, and you won't be that far wrong for that. But you have to go and read papers about what to do about Q rot and Q trans. Now, an important thing about this is I can calculate the ideal gas phase entropy without knowing anything about the condensed phase behavior. It's kind of peculiar because we talked before about the third law. Third law says what I'm supposed to do is do calorimetry of the solid at 0 Kelvin and heat it up until it melts, and then until it vaporizes. And I'm supposed to do calorimetry the whole way, measure the heat capacity the whole way, and then do some complicated integral. And then I get the entropy of the ideal gas at my temperature. But this thing just gives you a formula. Boom, I just type the energy levels into the molecule. Boom, it just tells me what the entropy is. So this is a very peculiar thing, that you can just, from the first principles, calculate the ideal gas entropy in a completely unrelated way to the normal way we would compute the entropy experimentally. And we can do this actually not just with quantum mechanics, but we can even just do it with the real vibrational frequencies. We know the real moments of inertia and the real vibrational frequencies, which we can get from spectroscopy. So we do rotational spectroscopy with microwaves, and we can do vibrational spectroscopy with infrared. We can get all the frequencies, all the moments of inertia if we need to. We can do it, and we can actually plug them into the Qs and get a value for the entropy. And so here's an example. This is for methane. If you look up in the NIST webbook, there's the link at the top there. This is what you'll find. And further down, it gives you the vibrational frequencies. It has like names of what they are, stretches and deformations. And these are the frequencies in units of 1/centimeter. If you don't know what that is, talk to somebody afterwards who knows about it, because it's confusing. And here's the infrared value. They measure with infrared spectroscopy. Here's measured with Raman spectroscopy. Sometimes you have to infer things indirectly through Coriolis interactions. The spectroscopists are expert at this. They look at the pattern of the absorption lines, and then you can work back to what the vibrational frequencies must have been. It's not like you just read it off. It's a little bit more complicated to get it, but you can do it. And so people have done that, and then you can just use those to calculate, for example, the entropy, get some number, and pretty good. It's like 3 significant figures of errors in the fourth place. So you can do pretty high accuracy calculations of the S's, for example, just from the gas phase spectroscopy with no regard to calorimetry at all. It's kind of amazing it all works out. All right, So here's a quiz for you. So we have multiple ways to determine the entropy for a molecule, both experimentally and computationally. We talked about before, you can do calorimetry and do third law methods. You can do equilibria and do second law methods. And you can also do these quantum things, just the absolute gas phase entropies straight off from the formula of Q. It's basically from spectroscopy or from quantum calculations. So question number one, do you expect that the entropy number you compute in any of these different ways would actually agree with each other? So here's a question. How many of you think that they'll agree with each other? How many think they won't agree? OK. Do we have a reason why they were not going to agree? Yeah.
Maybe it depends on some reference point for zero.
OK, so in principle, it could, for enthalpies, for sure, it would depend on the reference point, right? And so methods that didn't have a reference point, you wouldn't believe they could match. But for entropy, it's amazing, actually. The reference point of S equals 0 at absolute 0 actually works. And so that's actually works out OK, which is astonishing to me, actually. Any other thoughts about why they might not agree? All you people thought they're not going to agree, but then you have no idea why. Okay, speculation. Any speculation on why they might not agree? Yeah.
Say assumptions and the initial guesses that are associated with errors.
OK, so like in the quantum methods, you make a bunch of approximations. And so therefore, because you make approximations, you won't expect the exact number. How about if you do an experiment and measure the entropy? Do you expect to get the exact number? How about if I did an experiment and measured the entropy? Would I get the exact number? I can tell you definitely not. All right, so when you do an experiment, you only get numbers to a certain number of significant figures. And it depends on exactly what you did. And then in this kind of case, if you did it experimentally, say with third law, you're measuring heat capacities that have errors at a lot of temperatures. And then you're computing an integral of these numbers that all have errors. And your final integral will have some error in it, right? There's some propagation of all those errors. If I use this formula, the ideal gas formula with the Q, then I have errors in the values of the frequencies, and I also have the errors that I'm assuming harmonic oscillator formulas for the Qs, and I'm assuming rigid rotor formulas for the Qs also. And so all those things are approximations, so they should have some error. So whatever I compute, always, I expect to have some error, unless I'm computing something like 2 pi, right? That should be exact. But everything else in life, you get a number, it always has an error, right? So never anything agrees. But then we just say, well, what does agree mean? What does agree mean? If I say that these two results agree with each other, what does that mean? Yeah?
Within your expected error.
Exactly, right. So to have a discussion about this that's rational, we have to define what our expected error is, right? What's our error bar with the numbers? And if the two numbers agree within their error bars, then we say they agree. That's what we mean by agree. So whichever method you use to calculate the S, to figure out what the S value is, whether it's experimental or computational, you'd have to then also propagate along an error bar. And then you can check and see if they should agree. And in this case, the amazing thing is that they actually do agree within the error bars if you do it right. And you just have to make sure you keep track of all the errors all the way through. And then if you disagree by outside the error bars, then there's some problematic thing, like you converge to the wrong molecular geometry. You assumed it was harmonic oscillator when there was actually a floppy motion. You misassigned your IR band when you did the IR spectroscopy, and you have the wrong frequencies, right? All kinds of stuff like that. It can definitely happen. Your calorimeter got frosted up when you went down at absolute 0 and then misread something. Right? There's a lot of reasons why things can go wrong. So anyways, so that's it. The second law methods, where you measure the equilibria, so you determine an equilibrium constant by measuring the equilibrium concentrations. This one's has special kind of errors associated with it. So one is you need to have an absolute calibration for all of the species in the equilibrium. So let's suppose I'm talking about this. Be concrete. I have A plus B in equilibrium with C plus D. So if I want to figure out K experimentally, it's P, the partial pressure of A over P naught. No, partial pressure of C over P naught partial pressure of D over P naught over the partial pressure of A over P naught, partial pressure of B. Right, this is, so I need to measure the partial pressures of all 4 species. So I'll have a detector that can measure each of the species, but the response of the detector to each species will probably be different. So I need response factors for A, B, C, and D, which really means I need to know, somebody had to do a calibration at some point to calibrate what my detector response is to A, what my detector response is to B. So there's hidden behind this is a calibration problem. And when you want to do this, most commonly it's for when at least one of the species involved is unstable. So when you're trying to do a calibration of an unstable species, that's like already a massive headache. Okay, so you have some error associated with how you did the calibration. Because to do the calibration, you had to make a known amount of the unknown species, of the reactive species. So knowing how much you made. So there's another whole side thing called actinometry. There's like these kind of methods that are like methods to try to figure out how much of an unknown species you made. But those of you who are experimentalists, maybe you know what I'm talking about. It's like a total nightmare. But the rest of you, you'll glibly say, oh, thank God there's experimentalists who do that stuff. I don't need to worry about it. And it's all done. Okay, so somebody somehow figured out how to measure all these numbers all with plus or minuses, right? They have plus or minus some error, plus or minus. And the deltas are all different, probably. Okay, some of these things are stable molecules. I have great calibration. There's no trouble. Some of them are hard to measure. So I determine this. So now I'm going to get my K with some plus or minus some error, right? Because these errors propagate through into my experimental value of K. Then after I have K, how does the second law method work? It's going to be, what do I do here? Let's go over here. So the second law method says, first I have my K and I want to convert it into a delta G. So my delta G of the reaction is equal to negative RT logarithm of K of the equilibrium constant. So I put in my experimental number here with this plus or minus, right? And then this propagates through and gives me a delta G, 0, with a plus or minus something, all right? And then I think that this thing should equal to delta H of reaction minus T delta S of the reaction. And so I get this from somewhere. And so it has its own plus or minus. I measure the temperature with my own plus or minus in my experiment. And now I plugged in this value from my K, this value from somewhere, my temperature from my thermocouple, and boom, and now I have delta S plus or minus. Finally know what this is. And then I'm going to say, well, delta S reaction standard state is equal to S of C standard state plus S of D standard state minus S of A standard state minus S of B standard state. And I go look up in a table. Say I'm trying to determine the S of A. I look up in the tables and I find this value with its error bar, this one with its error bar, this one with its error bar, and now finally I can compute this one. This one has its error bar from here. And then I finally get my number I want. So this is the second law method of how to get entropy. So you can see, first of all, this looks like a total nightmare. Right? Okay? But people still do it. It turns out a lot of times it's actually the easiest way to do it, which just shows how hard it is to measure things. But you get this number, but what's special about this is you're not only sensitive to your own errors. So you made errors in how you did your calibration and how you made your measurement, and then you propagated it through, but you're also sensitive to errors in, say, the literature value for this and the literature values for C, D, and B. So here you're sensitive to previous graduate students who made these measurements, right? And so you have to worry about whether they reported their error bars correctly. And you're sensitive to that. So this is the kind of thing where you can pre-calculate before you do the experiment. You know you're going to be sensitive. Even if your error was 0, if you made this error teeny, so there's no error, you're still going to have error just because of these guys, right? So you can propagate and see how big your error is going to be in the best case, right? So then you can see whether it's good enough that it's worthwhile to do this experiment or not before you even do it. This kind of thing is where the number you get for one species depends on numbers you get for other species. This is a problem because if I had chosen a different reaction that involved A and done the same procedure, suppose I had done A plus X is in equilibrium with Y plus Z, I would have done the whole similar thing and end up with a different expression. But now it would be sensitive to the errors and the values for X, Y, and Z instead of B, C, and D. And so I could do that. And now I would have my number measured, computed two different ways, sensitive to different errors in the literature databases. Does this make sense? So this sets up the idea that there's sort of a network of errors. And then somebody else is going to take my number I publish, some other poor graduate student is going to do this and use A as one of their species and some others to determine the entropy of some other species. And this goes on forever. And everybody's dependent on everybody else's number. And if all the previous numbers published in literature are correct, we're all good. But most likely, they're not all correct.
For this error you're talking, why not use like the VNUQ to quantify your error? If you have enough
Yeah, of course, yeah.
database, you can use the VNUQ to quantify your error of each database. You can know this error bar for the prediction.
That's right. And if you do it using the original equation, you can propagate through and calculate what your error bar is in your essay. And now if I repeat the experiment, I do it with another one, I get an error bar from this one. But really what I should do is I should combine the two together. So that's the idea of UQ, is to try to quantify how all the uncertainties propagate through. Another way to look at it is Bayesian method. That after I finish this experiment, I have one value for SA. That's my current understanding of what SA is. And I can even write a probability distribution that the probability density for what SA really is some distribution. Because I think it's about here, but it actually could be anywhere in here. And I can even infer the shape if I know about the way I propagated the errors. And then if I do the second experiment with this one, I'll get a different number with a different error bar. And then, these both have to be true. So therefore, it's sort of the stuff that's in the middle is the stuff that's likely. And so I should have an error bar if everything is going well. Okay? So this is the idea of how to keep track of things. But it implies that you have to keep track of things in a pretty sophisticated way, because your numbers rely on what somebody else computed, and in turn, actually, what other people do relies on you. And sort of all the numbers together should all be consistent. If we think all the equations are correct, all the true values should actually satisfy all the equations. But the numbers we get from any individual experiment will not, because they all have errors in them. And so we have to figure out how to get the true knowledge out of everything we have. Now, historically, people did this by tables, where they just looked up the JANF table and read off the number, heat of formation of CO2 or whatever it is. And they didn't propagate the errors. They didn't think about how the fact that since the time the JANF table was published, somebody had done something else, which really should go back into the table and would change the numbers in the table, because the table numbers are not true forever, right? Every time I do a subsequent experiment, all the error bars should change, because I now know the number differently. But historically, our field has not been good at doing this. So historically, people just, somebody published the data, and then I read his paper, and I published my next one based on his number, and the next guy publishes based on mine. And it's very linear, and not considering the fact that there's these double checks that we should be doing between the data sets. So a big trend in the thermochemistry community right now is to try to go back and redo the whole thing in kind of a Bayesian UQ point of view, to be able to actually get the correct error bars for everything. And I'll show you in a minute that makes a gigantic difference. So far, that's not been done very much with the entropies, but it's been done a ton with the enthalpies, and I'll show you about that in a second. All right, and then I just wanted to ask, why do we care? Why do I care about the error bars? So this last question. If there's an error in a molecule's predicted S value, how is it going to affect your simulation? Yeah?
So then we can do a sensitivity to sort of see the impact of that variable on the overall kinetics, but you need to know where you can play around with that parameter, like what are the bounds.
Okay, so that's great. So if you have if you have your simulation, and you have the capability to do sensitivity, which you can do just by finite difference if you want. You could move your value of S up and down by whatever you think your error bar is in SA, just as a simple start. And then you can rerun the whole simulation and see what changes. And if you do it with analytical sensitivity things, you really want is like the change in the observable you care about the most. How much does that depend on this number? This S comes in multiple ways, so it's going to affect your final equilibrium distribution, but it's also going to affect the forward and reverse rates of all the species, all the reverse rate coefficients of all the reactions that involve the species, because they're all computed. The K forwards over K reverse is equal to Kc. It's the equilibrium constant in concentration units. And typically, this thing is related to the delta G of the reaction, which is computed using the S's. So if we have an error and an S, then the delta G we compute will have an error. If the delta G, if the reaction has an error, then the Kc will have an error. And what we normally do is we actually compute K reverse is equal to K forwards over Kc. So this Kc will have an error in it, and then that will cause K reverse to be incorrect. So then you have errors in every single reaction that involves the species A. The reverse rate coefficient will be incorrectly computed. So the errors can be very pervasive. Even just one number in the thermophile screwed up, in a bad case, it can really screw you up. And maybe in ways it might not be so obvious to you. So you have to watch out. Yeah?
So are the entropy, entropy is usually gotten from literature or calculated from the energy equation?
Most commonly, the enthalpies are from the literature, but I'll tell you, we'll go just about talk about that in a second, about where they actually come from. So the enthalpies are harder. So sorry? Yeah, the question was, do the enthalpies usually come from these kinds of equations or some other way? And usually some other way, which I'll talk about in a second. So these methods I showed you are actually turned out to be quite accurate for entropies and heat capacities, and are the way people usually do it. And historically, they did it from the IR spectroscopy and got the vibrational frequencies. In modern days, mostly people get it from density functional theory calculations. Sometimes they'll go to higher level theory to get the vibrational frequencies. And so that's the normal thing. And I would say in the last 10 years ago, the error in the entropy and the heat capacity was always negligible compared to the errors in the enthalpies. And so people spent a lot of effort to try to get the enthalpies better and didn't worry about the entropies and heat capacities because the errors were relatively small. Recently, the enthalpy methods have improved a lot. And now the errors from both the enthalpies and the entropies are approximately similar orders of magnitude. And so now I'd say it's your guys' job is to figure out how to do the entropies correctly so that we can get the really good numbers, because that's oftentimes now the limiting source of error. And in particular with the entropies, just beware about internal rotors and floppy motions. The normal equations I showed you are only for the harmonic oscillators, and there are many, many, many examples of molecules that you'll care about that have floppy motions in them. And also be aware that the tables are not the truth. So the table numbers were mostly derived a long time ago by people who didn't have good density functional calculations, who didn't have couple cluster calculations, and they just did the best job they could to estimate the frequencies, and oftentimes just use rigid rotor approximation to try to get a guess. And they typed it into NIST or into GenF, and every graduate student since has just photocopied it from that table, and they thought it was the word of God, that this is the truth. And it's not the truth. It's just, and if you read the footnotes, it's hilarious, actually. I had one like this. I was like wondering, where did this number come from? I read the footnote. It referenced reference 17. I looked at reference 17. In the footnote to that, it said, private communication from Joe Smith 1951, based on his estimate. So it was an estimate that a guy privately told somebody, got quoted in a paper, it made it into the table in the paper. The JANF guys, they looked up, where does anybody have this number? Oh, there's the table, has the number. Okay, take it. Put it in JANF. The numbers out everywhere in the whole world is using this number. That some guy in 1952, he just made his best guess because I think they were trying to make a rocket. They needed a number, so it's probably about whatever. So there's a lot of this, and the databases are highly heterogeneous in the error bars. So the error bars can vary by many, many orders of magnitude, but there's no warning in the database. They're all written to the same number of decimal places in the database, so they all look like they're equally good to your eye, but they are not. You have to read the error bars. And the NIST guys who publish the databases, they have a great saying. They say, we give you numbers for free. We're the government. We're funded by the taxpayers. We give you numbers free. However, for error bars, we charge. So always, always, always read the error bars, okay? And just try to remember, just because the number is in the table does not mean it's the truth, okay? That's, I would say, most common fallacy among graduate students is once it's made it into a table, a number is certified, it's official. All right, so we use the quantum chemistry. Let's talk about that. We talked about all this already, I think. The density functional theory is usually used for the second derivatives. Methods like these guys, pretty popular right now. It's a pretty rapidly changing field that people keep getting better density functionals. But even the older ones are still not that bad. Yeah. There's a nice database that NIST maintains that has computational chemistry results for a lot of molecules. More than 1,000 molecules are there. Many of them are ones that are important in combustion. And it has a lot of nice tools for comparing the experimental numbers for these molecules and the computational numbers. Often they have computations done at several different levels of theory. And it's pretty helpful if you want to get an idea of how good your computation should be at a certain level of theory, how big the errors can be. It also has a thing called a sick list, molecules with problems, where there's giant discrepancies between different calculations or between the calculations and experiments where no one's figured out why. That's also useful to look at. The ones where the calculation agrees very well with the experiment, if they were done independently, that's very reassuring, right? That you think the number must be right. If completely different ways both give you the same number for something, that's very helpful. And sometimes people have done two different experimental ways and they match up, and then you feel great. But when they disagree, then a lot of times you have a lot of heartburn. Which number should I use? Which one's right? Probably one of them had a mistake. Maybe both have a mistake. So you don't know. All right. This is what it looks like in the databases. So they have the calculated number. They have the experimental number. You can see the numbers are on the same page, but they're not the same. All right. Enthalpies for stable molecules are mostly pretty solid if somebody actually did an experiment. So if they actually synthesized, purified some molecule, put it into a bomb calorimeter, burned it up, measured the heat that came out, those instruments are pretty good. Main problem there actually often is whether they can make a pure sample of the original starting material. If they can do it, usually you can make it burn to completion and you can get a good number. But for radicals, which is half the species in the combustion model are going to be free radicals, you can't do it because you can't buy a bottle of radicals. So you have to figure out some more complicated way. And this is where they have to combine every kind of experimental data and computational data you got to try to overall bound the error and try to make yourself insensitive to the errors in any particular one. So you can measure, instead of measuring the equilibrium directly this way, another possibility is you can measure A plus B goes to C plus D under conditions where you have very high A and B and no C and D. And then you can measure the reverse rate, C plus D goes to A plus B, but where you start with just C and D and run it. And if you're fortunate, if these two rates are in this commensurate, you can actually measure both these guys separately. So you measure, this is like K forward, this is K reverse, and then you can use this formula, K forward over K reverse, to actually infer what Kc is. and then what K is and what the standard delta G is. And then you can go that way too. So some people do that, so that if you want to read a paper about that, there's an example in the JAX 1990, somebody did an experiment to try to figure out the heat of formation of methyl radicals, super important in combustion. A lot of the good numbers come from photoionization spectroscopy. So that's a method where you take a molecule, or actually a radical, and you irradiate it with an ultraviolet laser. And as you increase the photon energy, at some point, all of a sudden an electron will hop off the radical, and you make a positive ion. And then you have a mass spec there, and it detects a positive ion, or you have an electron detector, and it detects the electron. And you can tune the laser to exactly the wavelength where you see the threshold, where all of a sudden the electrons start to appear. And that's a very accurate measurement of the ionization energy, of how much energy it takes to ionize them. Then they do gas phase reactions of the ions, and those reactions are usually really fast, and it's easy to make them equilibrate. So they equilibrate them, and they can measure the ratio of the ion peaks. And that way they can get the equilibrium constant. And then they separately measure the other species, its appearance threshold. And from that whole thing, you can make a thermodynamic cycle to connect the two species together. And so it turns out to be a high accuracy way to determine the delta H's. Because what you're relying on as your measurement is the wavelength of the laser, which corresponds to the photon energy. And you can measure wavelengths to many, many decimal places. So that's a more accurate way to measure energetics than trying to measure actual heat released. You can't measure it that well. And then, of course, you do the quantum calculations. And by combining all these three, they ended up with a really high accuracy number, 0.3 kilojoules per mole. This is a really tiny error in the enthalpy of methyl radical. But if he was missing any of these ones, then the error bar would be a lot larger. So the fact that you have multiple methods to determine the same quantity that each have different error bars, if you put them all together, a lot of times you end up with a much sharper value. There's a very limited range of possible values that would actually be consistent with all the experiments. This is a lot of the radicals were measured by doing this forward reverse thing using iodide. So you have like a radical abstracts an H from HI, and then if you run a lot of iodine atoms into some hydrocarbon, you get a little bit of forward reaction. And by measuring those forward and reverse rates, you can get these equilibria this way. And that's turned out to be a way that's often used to determine either the enthalpy or the entropy, whichever is more difficult to determine. Oftentimes the enthalpy is to be the one. So this was a very popular method for a while to try to determine the radicals. And here's what the photoionization looks like. So you vary the photon energy, and they have a very good way to measure the photon energy very accurately by using a diffraction grating and by the wavelength of the light. And then you can see that the onset of when it starts to make some ions. And you can detect ions very, very sensitively. So you even make just one ion, you'll be able to detect it. And then the whole thing is about interpreting the shape of this initial curve here to figure out exactly where the threshold is. And that's where the error bar is. And mostly that has to do with the fact that some of the radicals might be in a vibrationally excited state. So they have some energy ahead of time. And they don't need quite as much photon energy to ionize as the other ones. So then they spend a lot of effort trying to cool the radicals before they irradiate them to make sure that all you have are cold radicals, not vibrationally excited, to do it. Here's the quantum calculations. We talked about that already. And then sometimes you can measure the equilibrium directly. So this is an example for the absorption of H atoms reacting with ethylene to make ethyl. Experimentally, you can measure the H atoms by atomic resonance fluorescence. And the shape of this decay, of the H atom decay, the signal, is a bi-exponential. And a bi-exponential is what you get when you have more than one reaction. If you only have one reaction, you'll get a single exponential. But you get a bi-exponential when you have this kind of thing where the H can add to this guy, but this guy can reversibly give back and give H. And so you get a there's a loss of H because it's diffusing out of your laser beam. But on top of it, it's disappearing initially because it's forming this, but then later this guy comes back and gives the H back. And the sum of those guys, if you solve the differential equations, it turns out to be a sum of two exponentials. If you can analyze and get the two exponentials out of your curve, then you can figure out the equilibrium constant. You figure out all the rate coefficients. And then you do this at a lot of different temperatures. And therefore, you can get how the K varies with temperature, and then you can infer the delta S and the delta H. The way things are reported, a lot of times are reported as these things called Ds. D of RH, which means, is defined to be the difference in heat of formation of the radical plus the H atom minus the RH. And it can be either the enthalpy at 298 or it can be at 0 Kelvin. And you have to read carefully in the literature what they mean. If they're good, they'll put a 0 here to warn you it's 0 Kelvin. And you can, once you know these numbers, then you can figure out. So there's a lot of tables. There's a CRC handbook. You guys ever see that book? Do you guys still use books? When I was a kid, we had books, big, thick CRC handbook. And the book has a table of the bond dissociation energies, a lot of common bonds. And that's pretty handy to keep track of. There's a nice, Berkowitz did a review article, has a nice big data set of lots and lots of different bond energies. It's very helpful for understanding which thing's going to be attacked first if you have a system, because the weakest bond will be the one that gets reacted first. All right, so the key advance in this field has been this idea that we should try to do this kind of UQ Bayesian approach, taking every source of data and try to all combine it. Instead of just taking the JANF numbers and sort of adding one more number to the table, we're going to go back and reassess. Every time we get more information, we'll try to reassess all the numbers and try to narrow the error bars in all of them to try to make sure that as we have more information, because the information we have about one reaction gives us information about all the species involved in the reaction, not just the one. So we have to kind of use that information to affect all of them. So then you have to make your tables active. It means every time somebody adds some new data, all the numbers in the table change. So it's completely different than the JANF idea. The JANF idea is like some brilliant person writes down all the great numbers, and all people do are photocopy it. And none of those numbers ever change, right? They're like written forever, etched in stone. You could just carve them on the side of the engineering building, right? They're always going to be the same numbers. That's not the view. The view of the active thermochemical tables is that all these numbers have error bars, and as we get more information, all the numbers are going to improve. So then the key is, how can I write a computer program that actually does that? It's kind of tricky, because you take a very heterogeneous data set, all different types of measurements and different types of calculations, all with different kinds of errors, and trying to figure out how to put them all together to consistently compute all the numbers. But the Argonne group led by Rushik has done it. And so they have a nice review article, 2004, about it. People have applied this thing to quantum chemistry as well, where you take all the quantum chemistry calculations and try to get rid of the errors in them by comparing all the numbers together. And just to show, so you get these networks of all different species that are coupled by different reactions. And we have estimates of the energies of all these different reactions, either from calculations or from experiment. And they all have to, you have to be able to find a set of numbers for the thermo of all the species that makes them all consistent. And you have more reactions than you have numbers of species. So it's always an overdetermined problem. And so you should do like sort of least squares. And it should be weighted because the error bars are wildly different sizes. So you have to weight the really precise data well, highly, and propagate the errors carefully. And then some of these things are coming from ionization. Some of them are coming from quantum calculation. Some of them are coming from forward and reverse rate constants. Some of them are from equilibria ratios. So, you know, some of the entropy numbers are coming from calorimetry. Some of them from a bomb combustion calorimetry. All different ways. So you get a complicated thing. So here's one, like they did a data set for computing the enthalpies of these species. These are super important in combustion, right? You're burning to make water, steam, right? That's like the common product. And OH is our most important radical. And H atoms actually drives the kinetics for making radicals. We'll talk about that in a minute. And so you need these guys like with super accuracy. And so they had all these data, you know, these numbers tell you which data they had about each of these different connections. Right, so here they had like 4 different experiments and theoretical calculations that connected water to OH+, for example. Would not be obvious, but there is. In the literature, there was 4 different numbers. And you know, there's all different numbers for all these different things. 3 different numbers for connecting the vaporization of H2O2. This is actually pretty hard to do, vaporizing H2O2, because it wants to decompose at the same temperature where it evaporates. So you can't just boil it. So you have to figure out some other way to make that measurement. Anyway, so they have all this data, and you try to put it all together at once and say, okay, now my massive least squares optimizer optimize the enthalpy values of each one of these guys all simultaneously, considering all the error bars. And so you get big, giant linear equations. And what happens is you get completely different numbers than GenF. So this blue thing here is the GenF heat of formation of OH. This is a very important number for us. And that's what GenF said. It said it was this number plus or minus this error bar. And then later somebody went along, Gurvich, and he says, no, the GenF's a little bit wrong. It should be a little bit higher, a little bit smaller error bar. But then these guys analyzed everything, and they decided that it was actually this little red thing here. So the number's much lower than the previous numbers, and also the error bar is a lot smaller. So now you get error bars that are down, teeny tiny. This change happened in 2001. This was like a nightmare for the kinetic modeling community, because it turns out that a lot of people had determined all of the energetics of the other radicals by reacting OH with the parent to make the other radicals, because OH is very reactive, so it was easy to do that experiment. But then all of the other radical numbers in the table were all actually implicitly dependent on the value of the enthalpy of OH. So then the enthalpy of OH means that almost all the other radicals in the model also had to have their enthalpies change to remain consistent with the experiment. But at the time this was done, nobody had active tables. So you had to go back by hand and erase your number you had in the table for this radical, put in the new number. And then you had to go look up about how this other radical's thermo, where it came from. Did it depend on the OH number or not? Which OH number did they use? So that was like a total nightmare. Around the same time, this group also recomputed the enthalpy of carbon atoms. This is a huge nightmare for quantum chemists because they always use atomization energies. So they're always using the energy of an atomic carbon as a reference, but that number was wrong. So all the quantum chemistry numbers were wrong. So that was a little bit annoying too. So this really brought home to the community how important this was to do this right. HO2, people sort of knew that HO2 was wrong before. So Janef had a number down here, and a lot of other people tried to remeasure it. So there were a lot of different numbers in the literature for this because nobody trusted the Janef number. And then now, by combining all the information, you get this little tiny error bar for HO2. And then you can see that when you compute, for example, the heat of formation using third law and second law methods, then they finally overlap with each other when you use the correct value. So that was like a verification that this new number was correct. And here's an example. So this is the HO2 radical. Its true number is 2.94 plus or minus 0.06. These are all the numbers that were in the literature. These guys went back and reanalyzed the experimental data as reported by all these people over here and said that actually the number should have been different because they didn't know about the new number of OH at the time that they did the experiments. So anyway, so it's a project. I guess maybe the comment is. And it's really important to try to make this automatic because not that many people are patient enough to go back into the old papers, reanalyze the old experiments, and get what the numbers really should have been. Also reanalyze how big the error bar should have been. Most people just trust whatever the experimentalist types in the front of the paper. Yeah, that's it, right? So, and then they went back to all this, like here's the old data. They found old data, and then they compared what their model would predict compared to with the new value compared to the old values and stuff like that. So that's the kind of thing you see. They also did it for the small carbon-hydrogen species. So this is one I was kind of involved in. And here you have to use the appearance energies from the ionization. That's what these TAEs are, and also some quantum calculations as well. And then carefully propagate the error bars through, as shown here. All right, and then this one is commenting about how currently in quantum chemistry, a lot of times people would do a single isodesmic reaction. They do a reaction. Let's go right how that works. So suppose I want to calculate the heat of formation of CH3. No, CH3 is too simple. Suppose I know CH3. I want to know the heat of formation of C7H11, no, 11, something like that. Okay? I want to know this radical. This is some C7H11 radical. I could do a quantum calculation of it. But I don't believe my quantum calculation is that accurate if I do atomization energies, because I know I have systematic errors in my quantum calculation because my basis set's not perfect. I'm using approximations. So a better way to calculate it is actually to compute the delta H of reaction for something like this. So this is a radical. This is a radical. And I can calculate each of these 4 species separately with my quantum method, and then calculate the difference in the energy between them. And by that differencing, I'm going to cancel out a lot of the systematic errors in the quantum calculation. And this idea has words like this associated with it, isodesmic. You're trying to find a reaction where the delta H of reaction is close to 0 because the bonds on both sides of the reaction are about the same. And because they're all about the same, the systematic errors in all those bonds will basically cancel each other out. And it's been proven multiple times this is a really great way to get good quantum numbers. Quantum calculations is you get much more accuracy if you can try to find ways to cancel out systematic errors, and this is a good way to do it. So in this case, I'm trying to figure out the enthalpy of this guy, and so then I would calculate all these 4, and these ones, if I have experimental numbers for all of them, this one would be, say, from bomb calorimetry, these 2 from active thermochemical tables, so they have very small error bars, and so then I'd be able to figure out the enthalpy. So many of the quantum calculations that you see for thermo, they would be done this way. This is how they would get the enthalpy. Professor Bazzelli from NGIT is famous. He's published tables and tables, lots and lots of species, free radicals, and done this. My group has also done a lot, some groups in Europe as well. And that's the standard way. But really we should do is do a lot of reactions that involve CH7H11 and make sure that they're all internally consistent. Because there might be something went wrong with this one calculation. And if I'm only going to I'm going to take an enthalpy value of this species based on just this one, I might be deluding myself about how good my accuracy is. So really I should find some other ones. I should say C7H11 plus C2H6 goes to C2H5 plus C7H12. That would be another one, right? And I could write a lot of other reactions that have C7H11 in them. And each one I could calculate them. If I calculate a whole bunch of them, then if I made a mistake in any one of them, it'll be diluted by the good ones. That's one idea. And also I might even be able to identify the bad one, because I might have a whole bunch of them that give me the same value of delta H, and one of them gives me some completely different number, and that will help me diagnose which of my calculations went wrong. So that's the idea. So that's what this neat idea, the network, is compute a whole bunch of reactions and then use them just like you would do a whole lot of experiments in the active thermochemical tables to try to determine the numbers. And then it shows you how to correctly propagate the errors and how to detect the outliers, all that kind of stuff. And so it's just linear algebra again. All right. You guys now are getting bored about how you calculate this. You believe it can be done. Now let's just talk about where you get the numbers. So a lot of people probably have already used this, the BERTCAT database. How many have used BERTCAT? Oh, OK. Well, the rest of you need to learn. So this is a really convenient database where it has a lot of good numbers in it. And BERTCAT's a combustion guy, and so he always tries to get numbers that are relevant to combustion. And you get this is what an entry looks like. So at the top, it says something that's basically telling you about what he did. And then there's the moments of inertia at the top. They use the rotational part. Farther down are the NASA polynomials, if you just want to use those. But there's information here about how he got the numbers and then the actual NASA polynomials that you want to use. And there's a lot of databases like this. And particularly, I wanted to show you this one, the active thermochemical tables one, because this is the one that's certified. All the other ones you look at, you have to do some project to figure out what the error bar is. So you get numbers, you get NASA polynomials, but who knows how accurate they are. But this guy, the active thermochemical tables, This one really tells you. Let's see if we can make it show. Thermochemical data. Come on. So you can see that the URL at the top, atct.anl.gov. And this is a list of 1,200 species, 1,199 species. And you type in your species name you want to look up the thermo for. So let's try CH30. So is that going to work? Come on. That doesn't work. Species formula, sorry. CH30. And there it is. And there it is. So there's two different C3HO species, hydroxymethyl and methoxy radical. And there's the delta H's at 0 and 298. And there's the error, plus or minus 0.3 of a kilojoule, which is less than 0.1 of a kcal. This is a very, very high accuracy numbers. And then if you click on the species, like say methoxy, it'll draw a little picture of what it looks like. And then it'll tell you the top contributors. So in this database, it's a network. All of the species are connected. Every species depends on every other number of every other species. So they found the best values of the enthalpies to be consistent with every piece of information they have about every reaction of all the species. But then they can, when they diagnose, which of these reactions are really affecting the number. So which ones are you sensitive to? And here they find out that in this case, methoxy is 7.8% of, what's going on with this? That's amazing. Okay, I won't point. So you can look at the top and see that the first reaction is a reaction of methanol with fluoride anion. So that was done in some mass spec experiment, and that contributes about 8% to the number. And then separately, there's Osborne apparently did a dissociation measurement. I don't know how he did that, of methoxy to methyl plus O. It'd be worthwhile to read the paper. And then a whole bunch of people did the bomb calorimetry of methanol. They burned it. That's a pretty important number. And another guy did a spectroscopy dissociation experiment with methoxy falling apart to form formaldehyde plus H, and so on. So all different types of experiments and some calculations too. And then the right, it gives you the reference for each one of them, and then what they think the error bar was, what they measured. So this is like a careful story about every piece of data that's in this huge network of database, and then where the numbers come from. And by combining all this different data, you can find that there's a very limited range of values that will be consistent with everything. It also can detect if there's outliers. If there's like one piece of data that just can't agree with everybody else, it detects that. And then those would be the ones that the poor, hardworking people at Argonne would go back and read the paper carefully and figure out what the heck went wrong and why is the number incorrect and reanalyze the experiment. But then if everything's consistent, they say, OK, good enough. They just use it. So that's how this works. And I would highly recommend that you look at this. And if you want really good numbers and you really believe the error bars, this is where you can get them. But unfortunately, so far, they only have 1,200 numbers. So if you need species that are not in the active thermochemical tables, then you can go to Burkat, and that's more. I don't know how many, it's a lot, thousands of species is Burkat. And it's just a big flat table with bazillion species, on and on and on. I don't know how many, a lot. Goes on and on and on and on. Pages and pages and pages of NASA polynomials. And so anyway, so that's Burkat. And then if you really get stuck, and Burkat doesn't have it, and Webbook doesn't have it, and Active Thermochemicals table doesn't have it, and you need a number for a species, you can go to the RMG website at MIT. And here you go to molecule search. And let's try C. Just help me out, guys. Is this right for methoxy? Yeah, I think that's right. Draw the molecule, make sure I got it right. There it is. And that's its molecular weight. And let's look for its thermochemistry. And it's going to say that it has a number from a DFT QCI calculation. QCI is one of those quantum chemistry methods. You have to look up about what that is. When it says DFT and QCI, you better watch out. What exactly they do? You have to go read about it, but you can read about what they did. But they got some enthalpy, entropy, and heat capacity numbers for it. Then they fitted it to NASA polynomials. GRI mech, they had their own value for this guy. Here's the numbers they got. Here's another level. This is higher level, CCSTT F12 with bond activity corrections. I think this should be really great. So that's my best quantum calculation. And Coran's, have you guys used Coran's mechanisms? Maybe like his heptane mechanisms, pretty popular. Anyway, he has a pentane mechanism. It had that species. It has the numbers in it. The USC MEC2 has some numbers for it. Another GRI MEC version has different numbers for it. FFCM1, that's the Stanford one, that has different numbers for it. Chernoff's model has different numbers for it. And group additivity gives us some other numbers for it. And here's a plot of the heat capacity of all these different methods. And you can get an idea about what the level of agreement or disagreement is between the different methods. This is a plot of the enthalpy and plot of the entropy. And you can see that the entropy methods, some of them disagree with each other. Right, so there's a gap here. Oh, come on. What's going on? Anyway, there's a gap of a couple of kcals per mole. How come? There we go. You can see between the two sets of data. So there's some discrepancy in the entropy for this molecule, but everybody seems to agree about the heat capacity and the enthalpy value. All right. So those are what you can do if you need numbers. And let's just talk very briefly, this tables of numbers. It's really helpful for you to just memorize the bond dissociation energies for a lot of common bonds. It'll help you understand what's going on in the chemistry. Group additivity. So the RMG website is, for most molecules, will just give you a group additivity value. And actually, if you look at Coran's models, if you look in Chernov's models, probably the numbers are mostly from group additivity as well. And group additivity is a Benson's method where it just noticed that the enthalpy is a linear function of the size of an alkane. And so then you can get the idea that, well, adding each extra CH2 group adds a certain amount of enthalpy. And so let's associate that number, that increment, with a CH2 group. And you can do the same thing for the heat capacity. It's also a linear function of the size. You can do the same thing for the entropy. Originally, that was all done experimentally. Benson published his book in the 1970s that observed this. Actually, he was published with a guy named Rick Buss, who later owned the Lakers. Anyway, his first graduate student decided to go into real estate after to get done to thermochemistry. That method originally was calibrated all with experimental data, mostly from stable molecules, bond calorimetry. He didn't have numbers for the radicals because nobody knew what they were, so he couldn't do the group additivity for those. But then, since the quantum methods developed, my group and Joe Bazzelli's group in particular have spent a lot of time developing group contributions that work for the radicals as well. And so if you go to the RMG website, for a lot of the radicals, that's what you would get is the group activity estimate. And so here are some of the programs that can do it. And if you want to read about it, there's a textbook by Benson that gives the original idea of this. And these are, generally, the functional group idea in chemistry, that big molecules act as like a collection of functional groups. If you know about the functional groups and add them up, you basically get the behavior of the molecule. There's some problems. So one is that the group contribution method really doesn't handle cyclic molecules very well. And there's a lot of technical problems related to doing that. And basically, there's a bunch of ad hoc corrections added to the models. Also, molecules that have complicated three-dimensional structure, where the three-dimensionality is important. The group contribution method is really, it's kind of flat. It seems like things are like a Tinker Toys, or like beads on a chain. That's the way it sort of adds them all up. And it doesn't consider the fact that this guy might curl around and interact with that guy. And so the three-dimensional structure matters. Usually group contribution will be wrong. And then there's some other species that have some problems. Actually, highly halogenated species is an example. All right, to summarize. So if we're in exhaust zone, we expect that most of the reactions are going to be equilibrated. And the key thing is to be able to compute the thermo so we can get the equilibrium. And in fact, you always want to know the equilibrium anyway. And you want to know the thermo because you can compute the reverse rate coefficients from the thermo. And we can get the thermo a lot of different ways. For the entropies and heat capacities, primarily it comes from statistical mechanics. And a lot of it recently is coming from the density functional theory with the rigid rotor harmonic oscillator approximation. You can also get a lot of things with group contribution methods with some error, but it's fast and easy. If you're willing to put a lot of effort in, you can get really good numbers, but you have to really consider error bars very carefully. And so the active thermochemical tables is like the best example there about very systematically considering all the error bars, what do we really know, making sure we have numbers that are consistent with everything that we know. And I think in the future, that will be used also for entropies, but so far not so much. And that's it. And it's time for break.